You're cruising at 35,000 feet, the sky is perfect, clear horizon. Maybe you've just closed your eyes. Then it happens, the aircraft drops. Not a gentle shudder, a lurch. Your armrests become life rafts. A coffee cup shoots across the aisle. Somewhere behind you, someone gasps. And in that half second, your brain fires the same thought it always does. The plane is falling apart. But here's the thing that makes this story genuinely strange. That feeling, that absolute certainty of danger, it's almost entirely wrong. Not slightly wrong. Deeply, fascinatingly wrong. And understanding exactly why is one of the most elegant stories in modern engineering. So why does turbulence feel so dangerous? Because every instinct you have says sudden, violent movement from a vehicle equals failure. That logic works fine on the ground. A car shaking violently, something's wrong. A building that sways in a storm, time to leave. But here's what changes everything. Air is empty. It behaves like a fluid, a living, churning, invisible ocean that your aircraft is swimming through at 900 kilometers per hour. And that ocean has currents, updrafts, downdrafts, invisible standing waves called mountain wave turbulence, pockets of clear air turbulence, zones of violent motion with zero warning showing up on no radar. Early aircraft engineers learned this the hard way. In the 1920s and 30s, designers built planes that were rigid and strong, the way a steel girder is strong. They thought stiffness meant safety. They were wrong. When those planes hit sudden air loads, the forces didn't spread out. They concentrated at joints, at attachment points, at the worst possible places. Wings failed. Fuselages cracked. Disasters followed. So the real challenge wasn't how do we make planes stronger. The challenge was far more interesting. How do you build something that survives an invisible three-dimensional storm at altitude, at speed, every single flight? The answer sounds almost counterintuitive the first time you hear it. Planes don't fight turbulence. They ride it. Think about what turbulence actually is. Moving air. You're specifically air moving up and down in unpredictable pockets. When a plane flies through one of those pockets, it doesn't fall. It gets carried, lifted, or pushed down by a mass of air with real momentum behind it. That sensation of dropping, that's not the aircraft losing lift. That's a downdraft momentarily pushing the entire fuselage downward before the wings re-establish control. You're on a wave, not falling off a cliff. Now, here's where the engineering gets genuinely beautiful. You'd assume a commercial aircraft is built like a vault, rigid, immovable, solid. After all, it weighs up to 400,000 kilograms and travels at near sonic speeds. But the opposite is true. Aircraft are specifically engineered to flex. Think about a dry twig versus a green sapling. Snap the dry twig. It breaks instantly because all that force has nowhere to go. It's rigid. The energy concentrates at one point and it fails. Then the sapling. It absorbs the energy, disperses it through the fibers, bends dramatically, and springs back. Aircraft wings are the sapling. During severe turbulence, the wingtips of a large commercial airliner can flex up to 7 to 8 meters, roughly the height of a two-story building, and return to shape, completely as designed. The material science behind this is meticulous. Modern aircraft use combinations of aluminum alloys and carbon fiber composites. These materials aren't chosen just for strength. They're chosen for specific, predictable flexibility. Engineers know exactly how much a wing will bend under a given load, and they design for it intentionally. Before any commercial aircraft enters service, it undergoes extreme structural testing. Wings are physically loaded past their operational limits to 150% of the maximum certified force until they finally fail. Engineers need to know exactly where and how failure occurs so they can guarantee it never happens in normal operation. So that shuddering you feel at 35,000 feet, every flex, every creak, every uncomfortable jolt. The aircraft is doing precisely what it was designed to do. Once you understand this principle, design for flexibility, not rigidity, you start seeing it in places you'd never expect. Take suspension bridges. The Golden Gate Bridge can sway nearly 8 meters horizontally in strong winds. That's not a flaw. Engineers deliberately designed it to move, because a completely rigid bridge would accumulate stress until it tore itself apart. Flexibility is the safety mechanism. The Tacoma Narrows Bridge in 1940 collapsed precisely because it wasn't flexible enough. Wind created resonant vibrations the rigid structure couldn't absorb. It twisted itself apart, sate on camera, and became one of the most studied engineering failures in history. 2 bridges, 1 principle. One survived, one didn't. Skyscrapers work the same way. The Taipei 101 tower has a 660-ton steel pendulum called a tune mass damper suspended near its top. When the building sways in typhoon, winds, or an earthquake, the pendulum swings in the opposite direction, absorbing the energy and canceling the motion. The building moves, the pendulum compensates. Passengers in the restaurant on the 85th floor feel nothing. Now think smaller. A standard soda can is made from aluminum just 0.1 millimeters thick, thinner than a human hair. Yet it withstands the internal pressure of carbonation without imploding. How? The curved surface distributes stress evenly across the whole structure, the same principle as an aircraft fuselage. Put a small dent in that can and it immediately becomes fragile. The dent creates a stress concentration point, exactly the failure mode that destroyed those early rigid aircraft. The geometry is the strength. In your car, every time you hit a pothole, your suspension system absorbs that shock through springs and dampers. Controlled flexibility that prevents the chassis from transmitting the impact directly to you. Remove the suspension and every pothole feels like a turbulence event. The pattern is everywhere. The most durable structures in the world aren't the most rigid ones. They're the ones that absorb and distribute energy rather than resist it. Turbulence engineering is just this principle operating at its most extreme scale. 400 tons of aircraft moving through invisible chaos, built to bend so it never breaks. Now, this isn't a story where engineering solved everything cleanly. There are real trade-offs. More flexibility generally means lighter materials. Lighter materials cost more and require more precise manufacturing. The carbon composites in a modern Boeing 787 are extraordinarily capable, but they're also extraordinarily expensive to repair. The flexibility that makes passengers safer also makes maintenance more complex. There's also what engineers call the comfort paradox. A theoretically maximally flexible aircraft, the safest possible structure, would feel unbearable to fly in because passengers would feel every single air movement. So engineers balance structural safety against passenger experience. The result is a carefully tuned compromise, flexible enough to survive, stiff enough to feel stable. And turbulence, while rarely dangerous to the aircraft, is not harmless. Flight crew injuries from severe, unexpected turbulence do occur, most often to people not wearing seatbelts when the aircraft hits a sudden pocket. The aircraft handles the physics. The risk, when it exists, is human. Finally, our nice clear air turbulence, invisible to radar, occurring in perfectly clear skies at cruise altitude, with no visual warning whatsoever. Research suggests it's increasing as climate patterns shift, creating more instability at the altitudes where commercial aviation operates. The engineering to survive it is excellent. The forecasting to predict and avoid it, still catching up. So the next time the plane drops, and it will, try to hold 2 thoughts at once. 1, yes, it's uncomfortable. Yes, your body is wired to treat sudden motion as a threat. That response is ancient and it's real. And 2, the structure around you has been tested past its limits, built from materials engineered to bend without breaking, and designed by people who spent careers understanding exactly what happens when 400 tons of aircraft meets an invisible ocean of moving air. The shuddering isn't the plane struggling. The shuddering is the proof it's working. You're not in a fragile machine fighting chaos. You're in one of the most carefully designed flexible structures humanity has ever built, riding invisible waves exactly as planned. And now that you see it, in bridges that sway, in soda cans that curve, in skyscrapers with pendulums, in wings that flex 8 meters and spring back, you'll start noticing the same idea everywhere. The world's most durable things don't resist force. They move with it.